So we just took a look at the memory layout within a process, and we saw that there are two locations or two regions of memory that are allocated specifically for the program to put dynamic content at runtime. We spent a certain amount of time talking about the stack, but we introduced a new region of memory called the heap, which is also a region where we can allocate stuff. And when we're talking about the heap, the thing that we're interested about in the heap is dynamically allocated memory. So if, for example, we want to load some data from disk into memory, and we don't know how big it is, the heap is a good place to put it. And the way we are able to do that is with two standard library functions that we have. So the details we can see here in the man page for the malloc function. And the two functions that I'm talking about are malloc, which is going to take a size in bytes, and then it's going to return a pointer to a region of memory allocated on the heap of the size requested. And then when we're done with heap memory, we need to pass that pointer that we got from malloc back to free. Or we need to pass it to free, which gives it back to the runtime where it can put it back on the heap, where then we can use it again in the future. So every pointer we get from malloc needs to get passed to free exactly once. There's a couple ways that this can go wrong. So if we allocate memory with malloc, and then we don't pass it back to free, then it's not returned back to the heap for future use. And if we keep calling malloc and don't call free, eventually we'll run out of memory. The other possibility is if we call malloc once, and then take that pointer we get back and call free on it twice. That's going to result in the horrible problems. We'll talk about exactly what those horrible problems are more when we talk about how to implement malloc and free. We'll be doing that for a future assignment. But for now, it's sufficient to say that what double free does is it corrupts the heap. So your program's just going to randomly crash, probably on a future malloc, but maybe just randomly. So the other thing is free. So void takes a size and returns a pointer. Free is going to take a pointer and return nothing, because that's us giving back memory to the operating system. So that's how we're going to deal with the heap. But that raises a question. Is there some way that we can allocate dynamic amounts of space on the stack? And the answer is that there is. There is a function called alloca. While it looks like a function in the API, it's not really a function, and this is actually something that cannot be implemented as a function in C. It's a magical thing that the compiler does. And what this does is it allocates a dynamic amount of space on the stack in the stack frame for the current function. And that's really simple to do in assembly, but it requires the special function or the special thing to do it in C. Alloca doesn't get used that frequently, especially now with modern C, where we can specify dynamic sizes for stack allocated arrays, but you'll occasionally, depending on what sort of programming you're doing, you'll occasionally see alloca in the wild. And when I do programming examples, I like to use alloca because it does exactly the thing that I want to talk about here. All right, so let's do a couple of examples that take advantage of this idea of dynamically allocated or dynamically sized blocks of memory. So the first example that I want to do is I want to write a function called SumArray, or I want to write a program called SumArray that has a function called SumArray. And as per usual, we're going to start in C, but now we're talking a little bit more about the behavior of C in addition to the behavior of assembly. So what this sum array function is going to do is it's going to take an array, x's, and then it's going to take the size of that array. I talked a little bit about this when I was talking about strings, that in C we have to null terminate strings because we pass strings, which are arrays of char, around as a pointer to the first element in the array. And if we just have a pointer to the first element in the array, we don't have the size. So if we want the size, we need some mechanism to find the size or the end or something. And so for strings, the mechanism that we use is that in C, strings are terminated by a null byte, a 0 byte at the end of the string. But in general, when we're just passing around random arrays, they aren't necessarily 0 terminated. So when we're passing an array to a function, the standard pattern is that we pass the array as one argument, and then we're going to pass the size of the array as a separate argument to the function. When we're talking about structs, we'll talk a little bit about the other option of packaging together the pointer and the size into one object. But just in generic C programming, this idea of taking a pointer to the beginning of the array and then the size is a normal pattern. All right, so to sum up this array, we want to go ahead and have a place where we're going to put the sum. Then we're going to loop through the array. So we're going to loop through each index in the array, n is the size. We're going to go ahead and add each element into the array, or each element of the array into our sum. So x's are our input, y is our output, like high school math. And then we'll write a main function. And the way this program works is you call it with a number, which is going to be the size of the array, and then it's going to read in the elements of the array one at a time on standard input. So we're going to type the numbers on the keyboard into the program after we run it. It's a sort of weird way to do it, but it's fine for this example. So we're going to go ahead and get that size from the command line. And then we need a place to put the array. So the most obvious place to put the array is to dynamically allocate it on the heap. When we don't know how big an object like an array needs to be when we're writing the program, then dynamically allocating it with malloc is the reasonable default thing to do. Now we just typed malloc, so we immediately want to type free such that the free will execute exactly once every time the malloc executes. How to do that is dependent on exactly how we're doing our memory allocation. Sometimes we're returning allocated memory from a function, in which case sort of the interface of the function is that then the caller of the function becomes responsible for calling free. But here we're just allocating and freeing in the same function, so we should do that. The number that we pass to malloc here is the number of bytes that we're allocating. Remember, malloc returns a void pointer, and what a void pointer means is it's returning a memory address, but that memory doesn't have an associated type. And in C, what that means is that we can assign that pointer to any kind of pointer we want, and that's just going to tell the C compiler how we want to use that memory, or how we want the C compiler to think we're going to use the memory, which doesn't necessarily need to be the same thing always. In any case, we're allocating space for objects of type long, so 8 bytes each. We're going to allocate n of them. So if we have 10, we're allocating 80 bytes. And then we're declaring that we're going to use that memory for an array of longs, which we're going to give the name x's. Now, we're going to go ahead and say scanf. What scanf is going to do is read from the keyboard something. In this case, it's going to read a long integer as a decimal number. So we're going to be typing in decimal digits. And then we want to put that into the x's array at slot II. But the thing that scanf actually takes as an argument is the address of a location in memory. And then scanf is going to read in the integer, and then it's going to stick that integer it got into memory at the address that we gave it. It doesn't care that it's an array. It could be a just local stack allocated variable, or it could be a global variable. We have to give it a memory address, and it's going to put the value there. Now scanf returns the number of items that it successfully read in. In this case, if it read in one item, we're happy. If it read in anything other than one item, then we're less happy. So we're going to call abort. And abort is a function that's just going to make the program immediately crash. That's convenient if we are going to run this in GDB, because when we call abort, we immediately crash, and GDB says, oh, you crashed at this line, and shows you where the abort was. That makes it different from like exit 1, which is sort of a normal exit even with an error code. Then we're going to go ahead and printf sum equals some number, where that number is the return address when we sum array on x's. So there's our program. Let's give that a try. It compiles. 1 plus 1 plus 1 plus 1 is 4. 1 plus 2 plus 3 plus 4 is 10. 4 plus 3 plus 2 plus 1 is 10. So our sum array program seems to work, at least with inputs of size 4. Let's try 10 and 8 ones is 13. Oh, I said 4. I meant 9. 10 and then 1, 2, 3, 4, 5, 6, 7, 8 should be 19. It's 19. Our sum array function works. So we're reading the values into memory, and then after we read them into memory, we're going to sum them up to produce a single sum. So that's some working with arrays in C. Let's go ahead and translate this into assembly. Again, I'm just going to copy it over into an assembly file, delete this stuff, comment out this stuff. I'm going to comment out the two functions separately because we're going to translate them separately, because that's how that works. There are three strings. So data. First one is usage message. Is a string. Usage is /sum array n. Next one is long format. Long scan. It's going to be a string. It's just going to be %ld. And then we're going to have out format is going to be a string, which was sum equals %ld new line. And those are our three strings. We also need global main, and then the rest of our program is going to be in the text section. Translating sum, we have variables. Now, alright, I can't put semicolons because assembly mode is annoying in Emacs. That's fine. So we have some variables here. First variable is x's. Well, I guess the question that we want to ask before we start thinking about variables is, do any of these things need to go in safe registers? Are there any function calls here? No. As written, this sum array function is a leaf function. It doesn't call any other functions. And so we can allocate everything to temporary registers. So then xs is RDI, NN is RSI, YY is RAX, because that's going to be the return value. We have II can be RCX, because C was the counter register back in the day. And I think that's sufficient. skeleton, sum array, enter 0, 0, leave ret. Everything's a temporary, so we don't need to do any stack allocation or pushes or anything. Of 0 to RAX. For loop. Our initialization, mov 0 to RCX. Two labels, sum array for cond, sum array for done. When we're done with the array, we always just return y, so that's not important. We're gonna jump to sum array for cond, and we're gonna inc the counter. Now we need to do the condition. The condition is we're going to compare II to NN. II is RCX, NN is RSI. And then if II is greater than or equal to NN, we're done. Sum array for done. Again, this is the sort of opposite question that we ask in the C code, because we're asking the opposite question. The question in the C is, do we continue the loop? The question in the assembly is, are we done with the loop? So then we have one statement here. We have an add. We want the result of that add to go in RAX. And then the first argument to the add is this thing, x's sub II. Now, conveniently for us, in Intel style assembly, there is a syntax specifically for array indexing. So because array indexing is always a loader store to memory, there are parens. The first thing we put in the parens is the base address of the array, the pointer to the beginning of the array. The second thing we're going to put in the thing after a comma is the value that we're indexing into the array with, the thing in brackets. And the third thing we're going to put in the array is the size of one element. So the size of long is 8. So this RDI, RCX, 8 is the assembly translation of this x's sub II thing in C. And that is a complete translation, I believe, of our sum array function. So let's go ahead and translate main. First we have to do our vars. Now we have a couple of vars here, and a couple of them do need to survive function calls. argc does not need to survive a function call. We only use it once, so it's going to be RDI. argv does not need to survive a function call. We only use it as an argument to A to L, so that can just be RSI. NN does need to survive function calls throughout the function, so NN is going to be R12. X's needs to survive function calls. For example, it needs to survive the scanf. Therefore, X's is going to be R13. II does need to survive function calls. For example, it needs to survive the scanf. So II is R14. Count does not need to survive any function calls, because it only gets used on the next line. So count can be RAX, since it's going to be this return value, and then we immediately use it. I believe that is all the variables, so that should work out for us. So our skeleton goes main, enter something something. Well, let's go ahead and push our safe registers. So push R12, push R13, push R14. That's 3 of them, so we're going to enter 8, 0, leave. Then we need to pop R14, pop R13, pop R12, that's reverse order, then we can ret. Now just while I'm here, we're going to mov 0 to RAX. And there is where I want to start thinking about body logic. So the first thing that we need is the ability to do a failed exit, because we want to return 1 in this argvk, or growing number of arguments thing up here. So we're going to ask compare 2 to RDI. And if we are not equal, we're going to skip over usage. So main skip usage. Otherwise, we're going to mov our usage message into RDI, call puts, and then mov 1 into RAX, and then jump to main done. So there's our usage block. If we don't care about the usage message, the next thing that we're going to do is we are going to call A to L on our argument. So we need to mov 8 RSI into RDI, call A to L, and then mov RAX into R12, because that's where NN lives. Next we need to do that malloc. So we're going to mov R12 over to... Wait, no. We have R12 in RAX, and RAX is one of the default places for multiplies. So we want to mov 8, which is size of long, into R10, which we didn't use for anything. R10 is just a temporary. Then we want to imul R10. That's going to give us the result of NN times 8, or NN times size of long in RAX, which we can then mov into RDI and call malloc. Once we call malloc, we get a result back of x's, so we're going to mov that RAX into R13, which is our x's array. Next we need our for loop, so we have mov 0 into R14, that's II, and then we need our labels for the for loop. The first one is main for cond, and then we have a main for done, jump main for cond, inc R14. So now we can write our condition, which is comparing NN. It's comparing II to NN, so NN comes first. NN was R12, II was R14. We continue if it's less than, so we end if it's greater than or equal to. Then our loop body says we are calling scanf. So we're calling scanf with 2 arguments. Mov long scan to RDI, mov. So the second argument is this address of x's sub II. Now remember that for x's sub II, we have this format here. So x's is R13, that's the pointer. II is R14, that's the index. And so if we wanted the value at that memory location, we would mov R13, x's, indexed by R14, elements are size 8, into RSI. but we don't want the value at that memory address. Instead, we want the address of that memory location. So if we want the address, we want to use the load LEA, load effective address instruction, which does the calculation as if it were going to do a load, but then doesn't actually request the value from memory. It's just going to put the result of this calculation for a memory reference, like this thing in parens, into another register. Finally, we need to move 0 into AL and call scanf. Now scanf returns a value. That value is going to be an RAX. So we're doing a comparison of RAX to 1. And if we don't like the result, count does not equal 1, so JNE call abort. Otherwise, we're going to keep going. So now we have to figure out what to do with call abort. I'm going to put call abort right here. Now, abort never returns, so we don't have to worry about what happens after we call abort. So cramming it in here between an unconditional jump and then the breakout of the loop label means that it should work out fine. Next thing that we need to do is after the loop, we need to call printf on the result of calling sumArray. So we're going to call sumArray first. The arguments are x's. So x's was R13, and then nn was R12. That's going to put that result in RAX. So we're going to go ahead and move RAX over to RDI, RSI, for RSI. Then we're going to move our output format to RDI. We're going to move 0 to AL. And then we're going to call printf to print out our result. That should be a complete translation. Let's give that a try. No pi o sumArray.s. Number of operands mismatched for mov on line 84. Bonk. We need to move RAX to RDI because we had just done that multiply. Once we fix that, we have sumArray 5. It's doing the wrong thing. So in main, we skip usage. If it is not equal, we want jump equal. So 1, 2, 3, 4, 5, sum together is 15. 10, 1, 2, 3, 4 is 14. 10, 20, 10, 20. 5, 5, 5. 40, 60, 70, 75. sumArray appears to work. So that's fine. Let me write a quick variant here. In this variant, instead of doing my allocation on the heap with malloc, I'm going to do it on the stack. So we're actually going to do two variants of that. First, we're going to do it the boring way, so long x is nn. That's going to do a variable length array allocation. The C compiler is going to allocate that on the stack for us. So 10 plus 15 is 25. That still works the same. The next version that we're going to do is we want long pointer x's. We want it to act like malloc, but we're going to call alloca on nn times size of long. So when we do an alloca, that's going to give us a pointer back, but that's going to be a pointer to our stack frame. So it's implicitly freed when we return. I need to include alloca.h in this case. And then we do the compile. 3, 1 plus 2 plus 3 is 6, so that variant works too. Now, from an assembly perspective, the version where we do a variable length array and the version with alloca are the same. They'll compile to the same code because logically they're the same thing. It's just the compiler is basically translating this thing into the alloca. So if we go ahead and copy sumarray.s to sumarray2.s, then we can go ahead and write the version of this that does alloca. Oh, I forgot something important. In sumarray, that's this one, before we return, we need to mov r13 to RDI and call free. Here's one of the things. If you forget to call free, nothing breaks. Your program is just wrong, and something later may break when it turns out that that's a memory leak or is otherwise bad. So let me just go ahead and run sumarray again. That is not what I meant to do at all. Alright, well, let me run sumarray again. gcc o sumarray.c. So that still produces 6, even with me freeing things. Sumarray2. This should not be calling free. We have 2 variants. The 2 variants were the alloca variant and the long x's and n variant. So I want sumarray2.s, and in here we're going to do not malloc, but alloca. And the way alloca works is, where's our malloc? Right here. So instead of calling malloc, we are going to sub rax, which is where the calculated value was from this multiplication, from rsp. So we've taken the stack pointer and we've moved it down to make more space. Then we're going to move rsp over to r13 because that's where we store the pointer. This is perfectly good, except for one minor problem. Let me go ahead and see if I can trigger that problem. No pi o sum sa2 sumarray2.big.s. So it assembles, no problem. sa2 4, 1, 2, 3, 4. That works perfectly. sa5. So when we call sa5, it immediately segfaults. sa6, 1, 2, 3, 4, 5, 6. That works. sa7, it immediately segfaults. So on even inputs, it works. On odd numbers, it immediately breaks. The problem here is stack alignment. There's a little trick we can use to force stack alignment. And hopefully I have it in my notes and I don't have to. There we go. So we're going to mov 15 to some temporary register that we're not using for anything. In this case, RCX is fine. Then we're going to not that value. Then we're going to AND RCX with RSP. And we're going to go ahead and assemble this and do SA2 of 6. Then we're going to do SA2 of 5. And everything works because now we have an aligned stack. So this, of course, raises the question, why does this particular code force the stack to be aligned? And of course, that's an excellent question. I'm glad you asked. So 15 in binary is the number, and we're talking about 64-bit numbers here because we're talking about registers, but I'm not going to type out a lot of zeros. 15 is the number that ends with 4 ones. Let's make sure that's correct. So this is 1 plus 3 is, 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. 7 plus 8 is 15. So 15 in decimal is in binary. 1, 1, 1, 1, plus some leading zeros. Not 15 is a bunch of 1s followed by 4 zeros in binary. That's what this not instruction does. It takes the value in the register and makes all the binary zeros be 1s and makes all the binary 1s be zeros. Just flips all the bits. So then if we do an AND, what that's going to do is for all the 1s in the RCX register, it's going to leave those bits alone in the RSP register. But for these 4 zeros at the end, AND is going to force the last 4 bits of RSP to be 0. So if RSP is divisible by 16, this does nothing, because if it's divisible by 16, then those last 4 bits are already 0. Otherwise, by zeroing out those last bits, we're rounding down that value to the next lowest multiple of 16. So it's like when we add an extra 8 into our enter instruction, except instead of having to calculate what the correct value is going to be, no matter what the value in the stack pointer is, anything, it can be off by 1, it can be off by 6. This is going to force the stack to be aligned, and it's going to force the stack pointer down, thus allocating more space rather than like overwriting things. All right, so that is my story on memory, the stack and the heap, the alloca function, or not a function, and how all those things work together in this particular example.